All right, so here's the next example on that page, and essentially in this example, you're just asked to predict the product. You're given a Lewis acid as the only reagent in the system, and this is the molecule that something is going to happen with. So to make this more like a test question, we could put like a box right here, and then wow, it's exactly like a test question. So I'm going to give you some hints right now, and then maybe you can do a little bit of work on your own to try and predict the product, and then we'll work on it together. So as far as the hints go, we have a Lewis acid right here. It's the same Lewis acid that always does Friedel-Crafts acylation or alkylation with alkyl halides. We have our alkyl halide right here. Usually we see that alkyl halide is separate from the benzene ring. Here it's attached, right? It's on the same molecule. But Friedel-Crafts acylation or alkylation doesn't have to happen intermolecularly. It can happen on one molecule. So this molecule can react with itself in a Friedel-Crafts reaction. So pause the video, try and predict the product. One more hint, there are going to be two products here actually. So do that and try and find both products and then turn it back on. So boop, boop. All right, good job, giving it your best shot. In this one we have an alkyl halide that is an acyl group this time, so this is going to look just like Friedel-Crafts acylation, which is very similar to Friedel-Crafts alkylation. First step, the halide is going to add to that AlCl3 to produce the superelectrophile precursor. And what we learned in class is that when you form this type of intermediate, this carbon-chlorine bond is going to break and leave and go to the chlorine in an SN1 type reaction. So when that leaves, you're going to have the carbocation be in that position right there. And one thing we talked about also in class today is we said, this doesn't look like it would be a very stable carbocation, but it turns out that it is. So there's a second structure that we can draw. There's something unique about this molecule as far as its ability to stabilize that positive charge. So maybe take a minute, pause, and say, what stabilizes that positive charge, and then come back. Boop, boop. Okay, so what stabilizes that positive charge? Remember that there's a resonance structure that you can draw, and hopefully you did draw that resonance structure where you show the electrons coming down to distribute that positive charge not just on the carbon, but also on the oxygen species. But in any case, that's why it's extra stable. That's why this goes by an SN1 type mechanism here where we form a carbocation. At this point, we have our benzene ring, and it turns out that two different products can form. So what are those two products? So this is a pretty advanced, pretty challenging question at this point in the chapter, so I wouldn't expect a lot of you to be able to just figure this out at baseline, but hopefully you at least got one of them. But we'll start out here. So this pi bond here can add to that carbon. Yeah, so it added to that carbon. So now what we have to think about is we attached this position here to that position there. So that means we're going to form a 1, 2, 3, 4, 5 membered ring that is attached to this ring. So we're going to form a fused ring system. So in doing that, we'll start out by just drawing that same benzene ring. And then there's a new 5-membered ring here, so we'll just draw that 5-membered ring. And then let's number our carbons so we know where to put things. So this was 1, 2, 3, 4, 5. So we're going to start in that same position. 1, 2, 3, 4, 5. Where was our carbonyl? It was at position 5. So we'll draw our carbonyl there. What lost a bond? We don't have our carbocation on here yet. Well, position 2 had 1, 2, 3, 4 bonds here on this structure. Now it only has 3. So position 2 is going to be where our carbocation is. And position 1 has this hydrogen atom that can be removed to reform the aromaticity of that ring. So the AlCl4 is now going to act as the base to deprotonate that hydrogen on carbon 1 here. This is carbon 1. And the electrons in that carbon-hydrogen bond are going to go and reform that aromaticity. So one of the products is this species here. Okay, what's our other product? Well, we saw carbon 1 attack, which was right next to, it's adjacent to carbon 2. There's no reason why this position couldn't also be the nucleophile. So let's draw a resonance structure first to show this. So if we move the electrons around the ring like this, we now have the electrons looking like that on that arene ring. And we can say the chlorine left, so now we have, so we'll actually draw a forward arrow. So forward arrow, the nucleophile, actually shoot. So we drew the chlorine leaving, that's this structure. A resonance structure of this structure is this resonance structure here. So it shows that we have a carbon-carbon pi bond between these two positions. So we can do the same thing. Start numbering over here. So 1, 2, 3, 4, 5. So we formed a 5-membered ring between this carbon and that one. Because of that, this methoxy group is in that same position. Now we're going to do kind of this arene, this alkene instead. So that alkene adds to that position. That's going to make a different constitutional isomer intermediate. So let's draw that out. So, and maybe this would be a good time to pause for a second and see if you can draw this out for yourself, because you should be after seeing how we did it for that one. So this is position 1, 2, and then we have a new 5-membered ring. 3, 4, 5. And where was the carbonyl? That's in position 5. Just notice that this is a little shadowy in here. Let's turn on the overhead light. So 1, 2, 3, 4, 5. So we've put the ring in the right spot, but now we need to do the same thing we did over here. Ask, where's our carbocation? Well, position 2 also, as compared to there, also lost the bond. So there's the positive charge there. There's that hydrogen there. So what needs to happen to reform our aromaticity? Instead of the AlCl3, well, not instead of, but as well as that is what happened here. This AlCl4, can deprotonate there and make the new bond there. So that would be the other constitutional isomer product. So what does that look like? Well, we're going to draw the product up here. So take a minute, make sure you can draw it yourself, but if we draw out the ring right there, now we have the 5-membered ring right next to that methoxy group. So like that. So these are our 2 constitutional isomer products. Again, this was a challenging question. It's your first time seeing an intramolecular Friedel-Crafts reaction, as well as now there are 2 regioisomers present. What if there wasn't a methoxy group there? If there wasn't a methoxy group there would only be 1 product, because the methoxy group wouldn't exist. So that is the same as that. So what made us form multiple products was the situation that we had that methoxy group there. So that is the answer to that predict the product question.